Thank you so much for inviting me here. Really pleased to have a chance to speak with you and enjoy this beautiful day, which I assume it's always like this down here. It's a little different. You got me out of Chicago, so I appreciate that. So as Xianyi mentioned, I am the director of our robotics center. We call it the Center for Robotics and Biosystems. So we're a robotics lab, but we do a lot of work in human-robot interaction and other sort of animal inspiration. That's where the biosystems side of it comes from. So I'm going to tell you a little bit about the Center for Robotics and Biosystems. I also refer to this other center, which is an engineering research center from National Science Foundation. It's headquartered inside the Center for Robotics and Biosystems, so they kind of overlap with each other. But it should be clear which one I'm talking about at any given time. I'm in mechanical engineering and have a courtesy appointment in computer science. So these are the Northwestern core faculty in the Center for Robotics and Biosystems. I'd say our center of mass, and I can almost reach, our center of mass is in mechanical engineering, but we have faculty from several different departments and even schools. So we have faculty in the medical school. And we work a lot with the Shirley Ryan Ability Lab. It used to be called the Rehab Institute of Chicago. So it's both a clinical and a research facility for prosthetics and helping people recover from injuries and learn to walk again. And so we work a lot with them and human robot systems. In addition to these core faculty, we have about another 20 affiliated faculty who work in different spaces but collaborate with us a lot. This is the facility. We've got about 15,000 square feet or so of contiguous space and some joint facilities like a drone arena here and some robot arms that anybody can use. So in a maker space. So again, instead of those 12 faculty sort of replicating different facilities in their own labs, we try to share as much as we can and tear down walls. It's worked really well for us. The students sit next to each other, and a lot of the collaborations start through the students. But of course, like anybody, we're bursting at our seams, and when we need to grow, we'll have to figure out we already pushed out civil engineering here. I don't know if we're very popular with our neighbors, but it's good to have that problem. So these are some of the things that we work on. I have efforts in all of these areas: human-machine systems, swarm robotics, bioinspiration. I don't do much myself in soft robotics, except that things I build have springs. So is that soft? I don't know. And manipulation. But just because we only have about 45 minutes for the talk, I'm going to focus today on manipulation. And again, to just put a little structure on the talk, I'm going to break manipulation into two categories. One is autonomous, and the other is human collaborative. And when I'm talking about autonomous, I'm mostly talking about sort of manipulation of small objects at the hand level. When I talk about human collaboration, I'm thinking about larger manipulation where humans and robots together perform the manipulation. And I'm going to start with the human collaborative side. And we're not doing anything specific to logistics, but everybody understands Amazon warehouses to some extent. So I'm going to ask you to keep that in mind. So you've got lots of things moving around in a warehouse, and you want robots to help you do that. So when I think about manipulation tasks for the purposes of this discussion, and by the way, feel free to raise your hand and interrupt me. I'm going to put manipulation tasks along 3 dimensions, and I guess I can't quite reach, so I'm going to use my mouse here. One dimension is the dynamic environment dimension. So down here, everything is static. We know we can model the warehouse well. Over here, you've got robots and people moving around in uncoordinated ways. This bulkiness dimension, are we manipulating small objects, the kinds of things that you usually get at your doorstep from Amazon? Or are we talking about large objects like furniture or appliances? And along this dimension, how precisely do we need to manipulate those objects? And in how many degrees of freedom? So down here, if I'm just transporting things from one place to another in a warehouse, maybe it's just X, Y, and the angle that I'm controlling. Over here, where I'm assembling things together, I need to control all the degrees of freedom with precision. So how do we solve these kinds of manipulation problems in this 3-dimensional space in a warehouse? So we have robots that can handle bulky objects and can handle things with precision, But generally, they're not very good in dynamic environments. So robots have light curtains around them, and they shut down if you get too close. So you see robots like the Amazon robot carrying a column of goods. That brings it over to a person, then it stops, and then the person takes things out. Or the stretch robot here from Boston Dynamics that can unload a truck. Again, if people get close, it shuts down. So when there's uncertainty in the environment or dynamics, then that's where humans usually come in, because humans can reason about their environment, make decisions. And so in the Amazon example, that robot pulls up, this person takes things out and then puts them in boxes and sends them to us. And if we're handling bulky items, so humans are not so good at handling bulky items by themselves, but you can give them tools to do it, like a dolly or powered industrial trucks like a forklift to help them manipulate large objects, but typically not with a lot of degrees of freedom or precision, right? So the forklift up there is for moving large loads from one place to another, but not precision manipulation. Right? So then the question is, what do we do in this octant of the space here, where we want to have precise manipulation of bulky loads in dynamic environments? And there's different ways we could do this. This is one of them. I'm putting humanoids up there just because they're so hot these days and there's over-investment in them. But in any case, a lot of excitement because they're so adjacent to AI, and AI is, of course, heavily invested in. But can we make robots that work better in dynamic environments so they can work around people and even with people? Humanoid is just an example. So pushing from the robot side into that octant. Another thing we can do is sort of push from the tools side for humans into that octant. And one way is that we can give people higher degree of freedom robot tools that they can interact with. So the exoskeleton is one example. You strap yourself into this, it makes you much stronger. Now I can help manipulate those bulky objects with precision that I couldn't before. So you could take it as an arrow from tools and trucks or an arrow from humans up into that spot. What we've been working on is a solution that we call mobile collaborative robots. So maybe many of you have heard of the word cobot before. A collaborative robot is a robot that's supposed to not shut down when it's around people. It's supposed to work with people, either in the same workspace or even physically with them. So we're going to do cobots, but we're going to make them mobile, and we're going to allow them to work in teams. So not just one at a time, but allow teams of robots work with one or even a team of people. By the way, I do work in exoskeletons also. I'm not going to talk about exoskeletons today, but just putting on and taking off an exoskeleton takes some time, right? So there's some drawbacks there. And there's also an inherent safety thing. You're strapped to a robot, right? So we're looking at solutions where you're not physically strapped to a robot. Okay, so I want you to envision factory, warehouse, or construction assembly tasks where you're manipulating a large payload. So in the example that you see on the screen there, that's about a 35-pound, 15-kilogram PVC pipe assembly. So you're manipulating a large payload. In that case, you could do it, but it's not easy. The center of mass is likely to be far from you, and it's not easy to handle that kind of load. You could do it with 2 people or more. So think about large payload. Cases where it's advantageous to have distributed contacts. So if you imagine, for example, a turbine blade for a large wind turbine, and if you grab it in the center and try to move it around, the weight is going to be sagging, causing it to sag on the ends. And I've actually done this with this was stupid, but I was putting together a coffee table for my house, and I had to put a glass pane into it, and I picked it up by one end, and its own weight actually shattered it, right? So yeah, that was stupid. So, but in any case, sometimes it's good to have distributed contacts. So you want to avoid stress concentrations. You want to spread out the contact forces that you're applying. So maybe one large robot is not the solution. Maybe having more than one that can collaborate. And we're also thinking about tasks that are difficult to automate. Okay? So maybe you just don't do it that often. It's not worth trying to automate, or the environment is dynamic and you can take advantage of the human's input there. If you imagine that we're going to build a structure on the moon someday, a station on the moon, I can imagine robots cooperating with people to help build that. This is not something you'll do thousands of times. So how do you make robots that work well with people? So we're interested in cases where multiple robots can come together, help a human do a manipulation, and if the object is larger, I can call over more robots. So basically it's swarm robotics, but now we have direct physical interaction through a payload with the human. So just to show you, so this was a demo we did about 2 years ago at a conference in California. So taking it outdoors was a little scary for us. And also the demo that we happened to choose was something that looks like a miniature plane wing, and it was windy, so the wing tended to blow away. But on the day that this video was captured, it was not windy. So my PhD student here is just showing us that she can manipulate this also about 40-pound plane wing with just a light touch. And she can manipulate in all 6 degrees of freedom. So she's not, the robots are basically canceling gravity for her, and all she has to do is provide the acceleration forces to cause the manipulation. And the forces of gravity tend to dominate most kinds of quasi-static manipulations we do with large loads. So the example I'm going to show you here and spend some time on is how to get a group of robots to do a task like you see here and interact safely with a human. So I'm going to start out with some classical modeling. You have probably seen systems like this where I need to model where is everything in the system. So in this case, I got 3 robots. They have robot arms. They're manipulating a common whiteboard here. And the first thing you have to do is have a description of where everything is in the system. So I'm going to call that description the configuration Q. And some of the variables have to tell me where the payload is. And some of the variables have to tell me where the robots are. And so now I know where everything is in the system. So I'm going to write it as a vector. But of course, those are constrained. So I can't have the payload over here and the robots over there. They have to be holding on to the payload. So there's constraints. So I'll have closed loops in here, right? I can draw a loop from here up through the manipulator, through the object, and back down. So there's closed loops in the system. And maybe the wheels, if they're typical, like car wheels, give you non-holonomic constraints that say I can't slide to the side. Right? So I'm going to have constraints on those configurations and their velocities. So if you write all this out, just using your standard mechanics or dynamics formulation, you've got inertial forces, Coriolis or velocity product kind of forces, potential forces. These are the controls that you're allowed to apply. You have some feedback controller telling the wheels what to do and telling what the robot joints should be doing, and how those torques that you might command get translated into these degrees of freedom through a transmission matrix. And then this term over here, these are basically Lagrange multipliers that enforce the constraints. Okay? So for example, this lambda here, I expressed the constraints as a bunch of velocity constraints up there. This lambda is basically a force that makes sure that that closed loop is enforced throughout. So everything up here is just mechanics, right? Except this term. That term is usually running on your microcontroller. It's looking at encoders and it's commanding torques. So that's happening with a finite bandwidth. So you sense something moves, and then 100 milliseconds later, you send a different control to the motor. And so because that's active feedback control, you actually have the possibility of over-constraint. Right? So if you imagine these, just think of 2 robot arms holding on to a common rigid body. If you're trying to control the positions of them, telling them to go towards each other is either going to crush the body, damage the robots, or have some other unpredictable behavior. So we have to worry about this mechanical over-constraint when we're doing active feedback control. So if I want to have a team of mobile robots work safely with a human, what are some things that it has to satisfy? So first of all, I'm going to require passive compliance, because that active compliance, where I read the sensors and I control forces, that's always going to have some finite bandwidth. And during the time, the latencies, I may damage the object or hurt the human doing the interaction. So I'm going to want some passive compliance for the safety of the human and the payload. I want to be able to control all the degrees of freedom of the payload. And I also want to do good force control at the end effectors. So for instance, today I was just looking at Boyan's a humanoid robot with these low gear ratio motors, which are great for trying to do force control. Most industrial robots will have super high gear ratios, really good at position control, not good at force control. We're going to demand good force control from our manipulator, and that's also from safety. And also, if the manipulator is mounted to a legged robot that's giving you sloppy motion control, I should still get good force control out of the end effector. Okay. So so here's an example of a mobile manipulator. It's got an arm on the end. If I were to grab on the end effector and push on it, I'm going to demand some kind of passive compliance there. Right? It doesn't have to be feedback controlled. I'm going to feel that passive compliance. And I'm going to describe that by this matrix K, a 6x6 matrix that maps small displacements to wrenches. And if multiple robots grab onto a common payload, then basically I can express their stiffnesses at each manipulator in a common frame and add them up. And now when I grab onto that payload as a human, I feel that total stiffness coming from the robot, and that's that K. So some things I care about is, first of all, no individual stiffness should be too high, because I don't want to damage the payload. The stiffness that I feel as a human when I run into the object should not be too high, so these are limits on the stiffness. But if I also want to get good motion control, then there's a lower bound on how soft it should be. Right? So these are some constraints that a good set of mobile cobots should satisfy. Second thing is manipulability. So again, Q is the configuration of the system. I'm going to focus on the configuration of the payload, Q sub P. So the number of degrees of freedom of the payload, if it's a rigid body, is 6, XYZ roll pitch yaw. But if it's got internal articulations or flexibilities, then it's going to add to that number of degrees of freedom. So I would like to be able to control all the degrees of freedom with the robot. So I can take those equations of motion I had before, factor out those constraints, those Pfaffian constraints, and then I get this expression that tells me how the degrees of freedom of the system accelerate as a function of the controls that I have control over. And the key thing there is that F matrix that maps my controls U, the torques I command, to accelerations of the system. And I can break that F matrix up into two parts. A part that refers to how I control the degrees of freedom of the payload, and a part that says how I control the degrees of freedom of the robots. What I really care about is the payload. I want to be able to control all the payload's motion. So I'm going to call the manipulability of the system to be the rank of that upper submatrix. That tells me how many degrees of freedom of the object I can control. And I'm going to say it's fully manipulable if that rank is the same as the total number of degrees of freedom of the object. This is something that I want to satisfy. Okay, so should be passively compliant, should be manipulable, and last thing, should be good at force control. So here's some other systems I want you to think about as potential mobile cobots. You could have skid-steered robots or treaded robots or legged robots. All of those could be okay, even clambering over rocks, as long as their end effectors are giving me good force control. So there has to be some decoupling between the motion that's going on at the base and the forces being applied at the end effector. And that's really one of the keys to making a Mokobot work well. Okay, so this was our particular solution to that problem. It's intended for flat floors, so a mechanism wheel mobile base, and then we put on top of it a parallel manipulator called a delta manipulator. And the way that we're getting passive compliance is by using series elastic actuators. So we drive the 3 joints at the base, and it makes the platform move around in XYZ. And then there's also a passive gimbal at the wrist that allows rotation in any direction, but they're not controlled. They're measured, but not controlled. And so what that means is that one of these robots is good at applying a force through the center of its gimbal, XYZ force. Can't apply any torques because it's a passive gimbal. And here you see it moving around in 3 degrees of freedom, controlling the 3 degrees of freedom of the manipulator. And so what we're really trying to do is control the linear forces there. Okay, so just to show you those 3 points, passive compliance, manipulability, and force control for this particular design. Here you can see the passive compliance. So here the motors are locked And then all you're seeing is the stiffness due to the spring and then the mass of the robot. So you see this natural resonant frequency there. Manipulability, each robot only has 3 motors. So, if I want to control all 6 degrees of freedom of a rigid body, 1 is not going to do it. 2 doesn't do it either, because if you imagine having 2 of these gimbal wrists on a line, there's no way to create a torque about that line, because each of these gimbal wrists flops around, right? So I actually need 3. 3 is the minimum number, so I can control all the degrees of freedom of a rigid payload. And actually, I can control up to 3 more degrees of freedom of internal articulation. Okay, so that's why we built 3, because these take time to build, and we built the minimum number. And then in terms of force control, we spent a fair amount of time, making sure our series elastic actuators are pretty good. Maybe we get a bandwidth of 10 hertz or 20 hertz, depending on how you want to call it, of force control. So we're pretty good at force control, but still there can be this mechanical overconstraint that the passive mechanics have to pick up. So again, just a video of us doing force control. So here, actuators are off. Now we do active stiffness control. So this is us doing force control and making the forces proportional to the displacement of the manipulator. Okay, so now what can we do with this? With one robot, what we're demonstrating here is that the end effector's job is to try to keep 0 relative force with the human. Okay, so as the human moves around with a relatively light touch, this robot that weighs, almost 100 pounds is reacting underneath it. And the mobile base, all it's trying to do, think of this as velocity controlled. The end effector is force controlled. So while it's trying to apply 0 force at the end effector, the mobile base is always just trying to get under the center. Why? To maintain its control authority. Because if the end effector ever got to the edge of its workspace, it can't do force control anymore. So this is basically just following the end effector around. And also as the user twists it, then the robot will twist too, just to avoid, winding up the cables. Okay, so that's just one. Now, if we have multiple of them together, we can look at emergent behaviors. So if I have several of them manipulating the same object, they're just communicating mechanically through the object. Or I could have coordinated behaviors where they're talking to each other in a decentralized network or talking to a centralized coordinator. And what I'm demonstrating in this talk is just this. So there's no communication between the robots. The only communication that happens is because one moves or applies a force and the other one feels it. So with that, all these robots are trying to do is cancel the effect of gravity. So from the user's standpoint, it should feel like this object is floating in space. Now you'll see here the robots are doing a lot to try to make sure that the end effectors stay in the center of the workspace, but from the user's standpoint, it looks like the object is just floating. And so that allows, in this case, this 15 kilogram or so payload to be manipulated with a really light touch within the workspace. Right? So each robot has a limited workspace. So if the user tried to lift it up too high, it would be outside the workspace. But within the workspace, it feels more or less weightless. So this is just an example of an assembly task. The important thing so manipulating in free space, you could imagine just manipulating with a joystick or some kind of space ball or some other controller. But when you're doing an assembly like this, the force feedback is really important. So the human feels that and can adjust what they're doing to do this. I think it's about 2 millimeters of clearance here, this kind of fine assembly. And the force feedback really enables that. You can also do payloads that have internal degrees of freedom. There's some approximations that have to be done here because the payload is not a rigid body. But again, multiple people, multiple robots, objects with internal degrees of freedom. And the collaboration should be intuitive. And if this works well, the user shouldn't have to train on it for a day before they can use it. Okay, so what are we doing now? So right now, if we think about what does it mean for robots to do autonomous manipulation, one way to think about it on a spectrum is if they're collaborating with a human, how much of the total manipulation force has to be applied by the human and how much is being applied by the robots. So down here, we have humans only doing all the manipulations, so they're providing all the forces. With the Mocobots, as I was showing, they don't have to provide gravitational forces, but they have to provide the forces of assembly. But the robots can be watching what the humans are doing over time. So if you do the same task over and over, this kind of assembly task, then you can start being proactive. You can basically learn a policy to do the manipulation, and then eventually work towards autonomy. These robots are fully capable of being autonomous. What we're working on is just making sure that they work well with people also, so they provide a pathway from being useful tools to being autonomous systems. So this is something we're working on. I mentioned that these are capable of doing autonomous manipulation. So let's see. In this video here, the robots have acquired this payload, but they don't know where they are relative to each other, and they don't know how much it weighs or what its inertial properties are. So the first thing they do is they shake the object around, and after time, they can estimate where they are relative to each other, where the center of mass is, and what the inertial properties of the payload are. So here's the actual situation where the robots are grasping at 3 points. After shaking for a while, the estimate of where, so robot 1 is our ground truth, so it knows where it is. But where it estimates robots 3 and 2 are grasping are very close to the actual locations. The center of mass estimate is close, and then the inertial estimates are pretty good. I mentioned earlier that we think during assembly, it's very important to have this haptic feedback, force feedback. During free space motion, it's not so important. So we're just beginning to work with in human studies to really characterize the value under different circumstances. And then the robots that I described just now are a very specific implementation of Mocobots. But if I were going to use this in an Amazon factory, it would not have that form factor. So if we push forward on particular applications, how do you match the form factor of the robot to the specific applications? Okay, so jumping back to my hierarchy of manipulation here, I just talked about human collaborative. I'm going to spend maybe the next 10 minutes talking about autonomous manipulation. And I'm going to break that up into 3 categories. Non-prehensile, and by that I mean things like pushing objects or throwing objects as it rolls out of the hand, so you don't have a grasp. Then you have fixed grasp cases where basically you're controlling the motion of an object relative to the world by firmly grasping it in the hand, and then the arm does all the manipulation, right? That's like a power grasp like this. And then you have in-hand manipulation, where the fingers can cause motion of the object relative to the palm. And I think that I actually had a discussion with my students in the lab whether this is really an example or not. So who's used chopsticks before? Most of us. Okay. So I think that all 3 of these are present. So here's a case where the human is using chopsticks to push a steamed bun or something. Okay. So I think the way that I use chopsticks, and this is where my students disagreed, I more or less keep the bottom chopstick stationary, doesn't move, and then the top chopstick I'm doing a lot of manipulation with, kind of like a pencil. And then this is a fixed grasp, that's in-hand manipulation, and together the chopsticks are doing non-prehensile manipulation. Who agrees that the bottom chopstick is more or less stationary when you use chopsticks? Who disagrees? Who has that bottom chopstick moving a lot, just like they do the top chopstick? Okay, interesting. So it's about 50-50. All right. So I might have to not use this example, but this is true for me. I'll just say that. So I'm going to talk about in-hand manipulation because I think this is really interesting, and this is the focus of a lot of our work right now. This is a less controversial example. So if you're twisting the lid on a jar, notice how much relative motion is happening at the fingertips. So if I show you a drawing of 3 snapshots there, I can rotate the lid of a jar, more than 90 degrees without regrasp. But to make that happen, the contact patches on my fingers are moving significantly throughout. And by the way, the thumb here is shown like this, not how it appears relative to the two fingers, right? So from here over to here, the contact patches migrate across my fingers. So I have to control that kind of relative motion at the fingertips. So in-hand manipulation requires roll slide contact. So why is that? Because you're just, again, limiting the rigid bodies. If you know about Grubler's formula or degrees of freedom or any of that, then you know this has 6 degrees of freedom, which means my fingers would each have to have 6 degrees of freedom also for it to be able to track the object without having any relative motion at the finger. Of course, that doesn't happen. So we don't have fingers with 6 degrees of freedom, maybe 4, maybe 5 or less for robots. So that means if we want to do in-hand manipulation, we have to have roll slide. And we have to be able to manage it. And we should embrace that, right? Because we're getting extra degrees of freedom without building in extra motors. Okay, so buttoning a button is an example, writing with a pen, another example of in-hand manipulation. So the way that we think about it is that manipulation is a negotiation between the manipulator and the environment. Here the environment is just the lid of a jar. But if you're doing an assembly task, the environment includes whatever the fixtures are in the environment. The motors of your hand, or the actuators of your hand, provide some of the forces, but the environment provides a lot of the forces too, right? So if you take the view that I'm going to buy a robot hand, it's got 200-to-1 gear ratio motors at every joint, and it's going to tell the environment what's going to happen. That doesn't work, right? We need compliance. We need backdrivability. So our challenge is to have sensitive, adaptive, backdrivable, reliable control of compliant roll slide contact. So that's one of the major challenges of the autonomous manipulation work that we do. Backdrivable, what do I mean by that? I mean that if the environment pushes on my finger, it complies, and not just in a way where you hear motor go zzz, you know, as it moves back and forth, but actually is sensitive to the environment. Okay, so this is an NSF Engineering Research Center that was awarded in 2024 to focus on this problem. This is it's called Human Augmentation via Dexterity. So we want to make robots more dexterous, but we want to make them more dexterous so they can augment humans' ability to do work. So this is an ERC that's located at Northwestern, or headquartered at Northwestern, but we have partners at Carnegie Mellon, Florida A&M, MIT, and Texas A&M, and then some contributing effort from Wisconsin and Syracuse. It's a 5-year commitment initially with the possibility to extend to 10 years, and it's a significant commitment. But what is it that we're trying to do? Am I back? Yeah, I'm back. Okay. So right now you can buy robot arms. They're becoming a commodity, but if you want to get them to do anything, you have to put something at the end of them. And what do we do there? We typically put parallel jaw grippers or suction grippers, and then the purpose of those is basically to do what I showed you before. Keep the object stationary relative to the arm. All manipulation happens at the arm. But that prevents us from doing things like buttoning a button or putting a lid on a jar, for example. So our goal, it's a 10-year center. So our goal is that by 2035, a non-specialist will be able to take this system out of the box, set it up, having it do useful, tactile, sensor-based, backdrivable, compliant things within a day, and then something useful for their actual work within a week. This is a big project, so one of the things that a center has to do is recruit industry partners, both those who are providing pull, like often big companies that we need this capability, as well as smaller partners who are providing new technology that can push. And so these are some of the center partners we have to date. So we've got some of our industry members here, and then nonprofits up there. And the goal is to work with them closely to really understand the needs and make sure that we're producing solutions that will have a future societal impact. 3 research thrusts we're working on, basically the hardware, the AI and control, and the human interface. So the hardware includes things like tactile sensing skin and new actuators. The intelligence includes things like simulation, AI, behavior cloning, and basically transferring skills from humans to robots. And then the human interface, something that allows the human to easily deploy the solutions in their own application. One other big effort of this center is the system integration team. And the system integration team is basically to take the outputs from the research thrusts and bring them together in test beds. A research test bed and then application test beds that interact directly with our ecosystem. So we have 5 application test beds, 1 basically at each of our partners. 2 are in manufacturing and assembly. And so the question is, can we take bimanual dexterous robots and have them have an impact in a manufacturing setting? Another one is assistive home care, right? So there's a major need for more, manual dexterity and home assist, right? Aging population, the cost of having friends and family health care is enormous, right? So how can we make robots that can help people live life more independently? And then high consequence manipulation, this is things like manipulating radioactive materials or other high value materials where you don't want to have human contamination. And we also have a test bed for education. So this is the research test bed as it existed almost 2 years ago now when the center started. So in the top right, you can see the user interface. He's wearing a VR headset and haptic gloves. And so as he moves his head around, the robot's neck carrying the stereo vision system is moving around to track that. As he moves his hands, the robot hands move. On the ends of the fingertips here are tactile sensors. So if the robot makes contact with something, he feels that replayed onto his fingertips. And so the idea is that if this system feels or works really well, that operator should feel fully embodied in the robot system, right? That's what good teleoperation would do. And right now, it's pretty good at some things and really bad at other things. And the reasons that it's bad form some of the research agenda for the center. The other thing that we can do with this is because we know how the human is reacting to the sensor stimuli to perform their task, we can capture all that data and we can use it to train autonomous policies. So we're interested in both autonomous behavior as well as teleoperation. So I'm going to just talk for the last couple of minutes about intelligent dexterity, so this process of making the robots autonomous. And we're pursuing 3 approaches. The first one is data-driven. This is what everybody's doing now. So how do we do foundation models for manipulation, right? When we don't have access to things like forces and tactile information like we do for video and text. So how do we do data-driven approaches to dexterity? Can we use modeling? Can we push modeling forward? So purely understanding, the physics and using that to basically generate robot controls, or some hybrid of the two. So as an example of one of our data-driven, so this is a diffusion policy approach, a behavior cloning approach based on diffusion policy. And so what's happened here is that the operator has trained, we call our system DexNex, Dexterity Nexus. The operator has trained the robot to basically pick up blocks and move them from one side to the other. And this is a common occupational therapy task for evaluating people who are recovering from injury. That's one reason it was chosen. So after demonstrating, singulating a block in this clutter and doing this transfer maybe 200 times, then you use the data to train a policy. And now this is the autonomous rollout of the robot performing. It's not great. Performance is not nearly as good as a human right now. So what are some challenges? Oops. First of all, you have to have a human teleoperate, right? Then that takes time, and it's actually tiring to use the system for long periods of time. There's a lot of degrees of freedom. Each hand might have 20 degrees of freedom in it. So you're already at 40. Then you add on the robot arms and what the neck is doing. A lot of degrees of freedom. Most of the data-driven approaches are operating in much lower dimensional spaces. And then if I train DexNex version 1, can I use anything I learned on that on version 2 when the hands have changed and the robots have changed? So the cross-embodiment problem are challenges. We have the pure modeling approach. So this is just a tactile sensor we developed in-house. It's another camera-based tactile sensor. Basically, the fingertip is rounded, so it allows rolling manipulation. If you have a purely flat fingertip, you can't manipulate, or you can't manipulate some flat parts. So it's got a rounded fingertip, it's got a flexure built in there, and it's got a camera that's watching the displacement of the dome up here. So the camera is watching the dome displace, and because you know the flexure stiffness, you know how much force and torque is being applied through the flexure. So you get force sensing and contact location sensing. And then after that, and a whole lot of modeling, you can do really simple tasks like the one you see here. So this is 3 fingers in initial contact with a cylinder, and the hand palm doesn't move, but the fingers move, and you can make the lid twist. So the problem with this is that you need a full model of everything in the system to make this work at all. This is only for rigid bodies. If you can do the mechanics, what do you do about deformable bodies? Then things get complicated. So the approach you see here is only for rigid bodies. And then if things are modeled incorrectly or if there's unmodeled effects, it sort of all falls apart. It's fragile to that. So then we're also pursuing approaches based on using data and modeling together. So basically you do more efficient experiments to guide your robot learning, and then you extract more information from the experiments that you do. And this is just early work showing that this 4-fingered Allegro hand can continuously spin. So this is really at its heart a data-driven approach based on reinforcement learning, so sim to real, but it's being biased by what we know about mechanics. So that was just a really quick spin through some of the things that we're doing on autonomous manipulation. And I'm just going to conclude by saying our journey today was to talk about manipulation and look at 2 different kinds: autonomous in-hand manipulation and human collaborative manipulation. And the work that I presented today was funded by the folks that you see on the left and was the work of several Ph.D. students and master's students whose names you can see here. And I'll be happy to take any questions. Thank you.
Dr. Lynch, I'm curious about the Mocobots. If I'm a human and I'm trying to move the end of the robot, I'm going to feel a delay in response to a motion. So there's a vibration and damping element. I'm wondering if the responsiveness was part of your design consideration, if you optimized for that based on what criteria.
Yeah, okay, good question. So our idealization is that the manipulator is applying 0 force to you. So the only forces that the motors driving the delta are providing are those that needs to cancel gravity. And so if it worked perfectly, you would never feel any force. But of course you do, right? And so that's why we did this careful characterization of the force control. We're doing better with our system than we think we could do with a highly geared system. But there's still something, right? So you're feeling a non-zero force. It's relatively small for slow motions. And then the bigger delay is moving all the mass of the mobile robot, right? So I'm feeling a little bit of initial force. It's going towards 0 relatively quickly, but then slower on a lower time scale is the robot mass, which might be 70 or 80 pounds, adjusting its velocity control to try to keep the center. But I shouldn't feel that. Right? That's the part where our force control design is trying to decouple what I'm feeling from what's happening happening at the base of the robot. So we want the workspace of the manipulator to be as large as possible, so don't ever run against the limits. But then the robot has to be able to respond at least fast enough before you get to the edge of the workspace. Yeah.
Thanks for the amazing talk. So I'm also having some questions about the Mocobots. So when you talk about the formulation, the assumptions include things like the objects that's being placed on the robot. And also, you talk about scaling this up to higher degree of systems like humanoid or legged robot systems. Have you looked into cases where if you are picking up some objects and you have to go through that transition process, at the beginning you have to go out of the workspace or sort of have to go outside the range. what do you think are the methods we can kind of scale that up to even figure out how to, do I need 3 robots? Maybe I actually need more. And how do I figure out the perception now that if I'm having other sensors, right? And that can help me, maybe giving me more closed loop feedback through the control process. I'm just curious to hear your thoughts on that.
Yeah, so there's a lot in that question. I'll try to pull a couple of things out. So one is, how do you attach to the object in the first place? So what you saw in all of these videos, including this one, the object has been attached, then our experiments start, right? So we haven't been addressing the how do you acquire the object in the first place. The view that we've been taking is that now imagine a typical wheeled mobile base, but with a robot arm with 6 or 7 degrees of freedom on it. The idea is that the human grabs onto the end of it, pulls it over to the payload, and attaches it. So what does that mean? Is there a vacuum gripper there? Or is there a strap that goes around, or a clamp? That has to happen. But our thought is that that's what's going to happen. The human's going to drag the robot over and attach. And now the question is, did I drag over enough robots? Are they in the right place? Right? So if I don't know that this table has its center of mass over there, I might distribute my robots equally around it, but instead I should have had 2 here and 1 down there, right? That's a great question. So now we ask ourselves, should we have mobility at the grasps, not just a 6 degree of freedom clamp? Right? So if you can imagine the robots could, if it's a flat object, could the robots roll underneath it? Maybe they have a spherical interface and they can roll around underneath and find the place where they have an equal weight distribution. All good questions, all open questions for us. But the number one thing for us is in this current design, basically the object has to be on a rack and the robots drive up underneath, attach, and drive away. If we want to acquire things from the floor, then we're going to need larger workspace and more degrees of freedom in the manipulator.
Thank you.
Yeah.
I have a question about the teleoperation case. So some of that motion was a little bit clunky, but I'm wondering how much of that problem is due to control theory versus like just human perceived latency. Like if you're teleoperating and there's like your reaction time is 250 milliseconds, and then there's like a 50 to 100 millisecond latency, I would imagine that makes it pretty difficult to control that robot. And then there's also probably slippage of the actual sensors on the human body as well. So how much of that problem is actually on the control theory side?
Yeah, good question. So latency is a killer. And that's probably where the most just straight up software engineering went into the system, was driving that latency as low as we can. And so now we're talking about, the round trip between I sense something, I move, and something responds in the low tens of milliseconds. And that makes a huge difference. If it takes a while to react, then it's just extremely hard to use the system. So that's something that's improved a lot from the first version to what you're seeing here. The haptic gloves are a big issue. There's a lot of issues, right? So the tactile sensing right here is only at the fingertips, right? There are some things we do with only our fingertips, but very few, right? So we need contact sensing elsewhere. And then we don't have a way to transmit it back to the human. So the tactile sensing we have, the tactile display, haptic display, happens only at the fingertips. And then, bringing the hands close together or even close to contact with the table, they have to do that, right? They have to cooperate with each other, right? But these guys, the hands as they exist now, are not my ideal hands. These are, 200 to 1 gear ratio pulling tendons that have a lot of compliance in them, and they break. If I were to run that heavy robot arm with this fragile hand into the table, I break the fingers, right? So not in this case, we tend to use soft tables. We have, software controls that if the hands get too close to each other, don't let them get any closer. So you can see here that most of the tasks, the fingers are not intertwined with each other. They're keeping their distance, right? So we think it's critical to design both the hardware and the software. So we can't just take robots off the shelf. These are shadow hands. They're a commercial product. Those are ABB arms. They're a commercial product. ABB arms, even though they are technically cobots, are not meant to be back-driven, right? The fingers here, they're back-drivable because the tendons stretch, but none of it is intentional, right? So we have to do design of both the controls and the mechanics at the same time. And by the way, probably a lot of you know, lots of companies now working on robot hands. But the majority of them now are thinking about how do we make them human form factor, fast and strong, and not many thinking about how do we make them sensitive and compliant. Not zero, but not many. So that's within the purview of our center to design these together. I don't know why this keeps shutting off. Yes?
Thank you for your talk. I was a little curious on, so for one of the cobot experiments, you had like a hinge, the two
Yes.
forces hinged together. How would the robots recover from the loss of the degree of freedom of the hinge once you like fully open it?
Wow, did I show that? That's a great question.
Well, it opened and then the video shut.
Yeah, so in our case, we had 3 robots. 2 were grabbing onto one of the bars and 1 was grabbing onto the other one. There's a hinge between them, right? So for the robots to be able to control all the degrees of freedom of that system, they have to satisfy certain configuration constraints, which is basically they can't be collinear. So we showed there that we as the humans could straighten it out. And now all 3 robots' wrists are on the same line. They can't resist the torque there. So now the robots can't do that anymore. It's completely up to me as a human to provide that force because the robots can't do it. Yeah, is there anything else? Yeah, so those 3 robots could control up to 9 degrees of freedom, but if I put them in a line like that, even for that 7 degree of freedom, I've lost a degree of actuation.
Gotcha.
Yep.
Okay. Yeah, thank you for the very nice talk. So follow up on the hand question. So, like, what would be like the ideal robot hand you would like to have? Let's say in like 5 years, but in a more like practical way. Yeah.
So one of the things that our center is doing, so DexNext, as you see it here, we're going to update every 2 years. So we're basically going to, change hardware. Maybe not everything, but some things we're going to change every 2 years. And the idea is to track our progress on certain benchmark tasks. So one of them is to be able to pick up a lid of a jar and screw it on, any size jar, any reasonable size jar, buttons, right? So we're going to track our progress. So we think that improving the hand is one of the most important things we have to do. And by the way, if a company comes out with the capabilities that we want, we'll just buy them. We'll take that out of our. We will no longer have that in our research portfolio. I don't think that's going to happen. But the most important thing we want is never to miss any contacts. So if there are contacts somewhere in the hand, we always know about it, right? We need back drivability, and we need softness. So if you think about your own hand, like when you pick up a penny from the table, it's important to be able to apply stress concentrations, maybe with your fingernail, right? So sometimes you have to be able to apply forces in small spaces. But mostly large, soft contacts like we can achieve with our hands help with stability of manipulation. So we want soft, high tactile coverage, back drivable. Yes?
Just related to that, is it important that the hand has a form factor that it's human form?
Yeah, no, that's a great question. A priori, no. Lots of form factors could be, and by the way, this is why I like talking with Bo-Yuan and Xianyi about their approach to changing tools, right? So, for a lot of tasks, so what's the screwdriver, right? So a screwdriver is good at screwing screws and not much else. But for that, it's really great. But you have to attach to it somehow. We attach to it by grabbing onto it with a fairly general purpose manipulator. A robot could just have a dock and mechanically clamp to it and have a much stronger connection than we have. And so now I'm forgetting your question. Yeah, why does that have to be humanoid? Yeah, so it doesn't, right? So we would be perfectly happy to come up with a design that has nothing, maybe it's based on octopus tentacles or something that can do fine manipulation. So I don't have to move all the inertia of this arm around, like a 20-pound robot arm. I don't have to move that all around just to screw a lid, right? I want to be able to get fine manipulation with low inertia. So it doesn't have to be human-like. Advantages are that a lot of the built environment is for humans. So, tools already exist for human hands. We can transfer information from humans to robots more easily, like we're seeing in these examples. But, if we have good sim to real, and we can do co-design of a robot hand that can do these 20 tasks well, and looks nothing like a human hand, we would be very happy with that. But for now, it's good at extracting information from humans and also a lot of our built environment, which we have a huge investment in, right? Cabinet doors, tools, all these trillions of dollars worth of stuff around us are made for human hands. So that's an advantage to that form factor. But we're not married to it, no. Yeah.
I have a follow-up question about the Editorial. So in terms of the Mocobot, like it drives through a mobile base, plus it's a parallel manipulators. The potential issue with those parallel manipulators plus the mobile base with these Omni wheels is that it may be hard to, like, even though the control can be precise, it may be hard to do the simple reel because of backlash, because of how the ground contact can be different, and how the mechanical linkage can have some compliance and usage.
Mm-hmm.
So how do we deal with that? And is there a systematic way to approach it?
Yeah, so I think the question is, what's the fidelity of modeling we're demanding from our simulation so that we can transfer behaviors from simulation to the real world? And we're starting out assuming that we're getting pure forces from the end effectors of the robot. We're ignoring the rest of it. So each one of those robots is just a point force source. Of course, that relies on the control working really well. And so, the difference between that and what happens in the real world, will that prevent us from learning certain tasks? I'm sure it will, but we don't know yet. So I was just talking, again, Boyan saying that, it's hard. It was your robot, I think. It's hard having parallel linkages because we can't simulate them. That's because you're trying to simulate the constraints, right? But you could put a function in there that says, if I control this motor, this is what the whole linkage is going to do. And forget about the fact that you've got, those Lagrangian multipliers that I mentioned earlier. I'm just going to say this is what happens, right? So will that kill the sim to real? Maybe, because the real system has backlash and compliances that you don't model, et cetera. I don't have a great answer for that. But I do think there was actually a really interesting, I'm gonna pitch one of our industry members for the Hand ERC. They had a really interesting post recently, blog post. The company's called Origami Robotics. And they make a very low gear ratio robot hand, which as a result, the hand itself, when it's running, can consume thousands of watts. But that's the problem, right? So any of you built robots, the reason we put big gearboxes on them is so we can use lower power actuators and still get a lot of torque out of them. Their solution is to just pump lots of current through the motors. They made a better actuator, but pump lots of current through the motors, don't worry about it, and we'll see how far we can go with the back drivability we get when we have low gear ratios. So, but one of the interesting things about this post is they said, it is that gearbox, which usually gets ignored or can't get modeled well in simulation, that kills machine learning. Because the motors don't really know what's going on with the outside world, because that gearbox is a big wall for the data that's trying to get through. So, to your question, sim to real, if we ignore things like friction backlash, big gear ratios, et cetera, that's going to put a fundamental limit on how well these systems work. All right, well, thank you. Really appreciate all the questions.